Hey guys, so we're going to start our Unit 2 with a review on system of equations that you have seen in Algebra 1. So let's do a quick review. So a system, when you think of a system, you can think of more than one thing working together. So for example, you might have a stereo system at home with your TV connected to speakers, connected to a DVD player. You might have a computer system set up at home with connected to your monitor, to your router, to your keyboard, to your speaker. So more than one thing working together. And when we're talking about a system of equations, we're talking about more than one equation working together, containing two or more variables. And then when we talk about a solution, it's an ordered pair xy that satisfies each equation in the system and makes them true. So the solution is really where exactly are the two equations working together. And when we are graphing, that's where the point of intersection is, where the two graphs intersect. That is the solution to the system. A point that makes both of the equations true. So when you have linear equations, let's say you have a system of two linear equations, anytime you have two lines and you graph them, there's three possible scenarios that can happen. You could have two lines that are intersecting lines. So just in your notes, draw two lines that are intersecting. So here's my first line. And here's my second line. Right, if you got two lines that are intersecting, the solution is the point of intersection, which is right here. In this case, my solution is the ordered pair 2, 1. Okay, so when you have two lines, the first scenario is that they intersect, there is a solution. So we can classify this system of equations as consistent, meaning that it has a solution. And then we can also classify this as consistent and independent, meaning that it has exactly one solution. This is the only point where the two lines intersect. Scenario number 2 is you could have two lines that are overlapping, coinciding lines, or the same line. So you would have one line, you can draw any line again, and then you would have the second line right on top of the first line, and they intersect everywhere. They overlap. So when we think about their points of intersections, there are so many points of intersection. All of these are points of intersection, any point on the line. And so our solution now there's infinitely many of them. And we say that there are, and we can't list them all, so we just say that there are infinitely many solutions. Okay, and then when we classify using vocab, we say that this system of equations, of linear equations, is consistent because it does have a solution. So consistent means it has a solution. And dependent, meaning that there are infinitely many solutions. And then the last scenario is you could have two lines that are parallel. So just draw any parallel lines. So they should have the same slope because we know that parallel lines have the same slope. And I'm just gonna mark them that they're parallel, just like how we mark them in geometry. And so now if we think about the solution, if there are parallel lines, well then they never intersect, right? So in this case, there's no solution. Or the symbol for no solution is a little circle with a slash through it. And so when we classify, it's no longer consistent because it doesn't have a solution. We say that it is inconsistent. And all that means is that it has no solution. Okay, and then if it doesn't have a solution, then we can't talk about whether it has one or many solutions, so then we don't worry about the independent or dependent. So anytime you have a system of two linear equations, two lines, and you're trying to find the solution, that's their point of intersection. It's a point that satisfies both equations, a point that makes both equations true. This one right here makes the first line true, it makes the second equation true. And you've got three scenarios. Either there's one solution, there's many solutions, and we can't name them all, or there are no solutions. So let's take a look at how to solve a system of equations. There are three different ways to solve a system of equations that you might be familiar with. The first method is solve by graphing. So we just graph our equations and find a point of intersection, and that will be our solution, right? So the first one is nicely written in slope-intercept form for us. So we're just gonna go ahead and graph the intercept, which is at 4. And the slope tells me to go down 3 over 1, down 3 over 1, down 3 over 1, and I'm just gonna sketch my line. And then my second equation is in standard form, so if you want, you can certainly rewrite it into slope-intercept form by adding 3x to both sides. So y equals 3x plus 2, and my y-intercept is at 2. Slope tells me to go up 3 over 1, up 3 over 1, or I can go to reverse, and I'm just gonna sketch my line again. Off. Okay, so now it looks like my point of intersection, the point that satisfies both equations, is right here. Only problem is this point is kind of hard to identify, and that's one of the drawbacks of solving by graphing, is that when you're solving by graphing, it's nice when the two lines intersect at the corner of a grid, corner of a square, so that we can identify clearly exactly where that is. But sometimes you have intersecting lines and they intersect at a decimal, an order pair that has decimals, and it's not exact. So when we're looking at the graph, it's not always easy to identify clearly where the point of intersection is, right? So if I have to guess, I'm gonna say, I didn't actually graph this accurately, but this is my point of intersection, which, because I'm graphing by hand, is a little bit off, but it should have been, if I have to guess, x maybe 1/3, okay, and then y is going to be at 3. And we can check to see if that's right by substituting it back into the equation. And then sometimes if you don't graph accurately, then it's not going to be right. So let's check it quickly. 3 equals -3 times 1/3 plus 4. Is that true? 3 equals -1 plus 4. And -1 plus 4 is 3, so that works. The second equation, let's check it. -3 times 1/3 plus 3, is that equal to 2? That's -1 plus 3, and that is equal to 2, and that is also right. So I just guessed it because I kind of knew what it would be, but sometimes it's hard to see, and so we don't usually rely on this method to solve a system. We usually rely on more definite methods where I can clearly figure out exactly what that the ordered pair is. So we're going to look at how to solve algebraically. A review on substitution. So there's two ways to solve algebraically. There's substitution and there's elimination. And in substitution, the first thing you want to do is to isolate a variable. So I've got 4 variables. This x, this y, and this x. Technically, it doesn't matter which one you isolate. You pick an equation and you get one variable by itself. But some are easier than others to isolate. So when you're looking at these problems, always think about how to simplify this problem. Okay, so I'm going to choose this y because all I have to do is minus 3x, and the y will be by itself. So I'm going to start here. 3x plus y equals negative 2. I'm going to minus 3x. So y equals negative 3x minus 2. Or you could write negative 2 minus 3x. It doesn't matter because we're not really graphing here, so it doesn't matter whether it's in y equals mx plus b form. Okay, but if you like to write it like that, that's certainly fine. And then once you get the one variable by itself, then we are ready to substitute. So instead of y, since I know that y is equal to negative 3x minus 2, I'm going to replace the y in the second equation with negative 3x minus 2. You have to use both equations. So 2, instead of y, I'm going to put in the negative 3x minus 2, because that's what y equals. Minus 3x equals 14. Now we've combined the two equations, and now we have one equation with just x's, right? By itself, I can't solve either one of these equations because I have two unknowns. But now that I've used substitution to help me get one equation with just one variable, I can solve for x. So let's distribute negative 6x plus minus 4 minus 3x equals 14. Combine like terms, negative 4 minus 9x equals 14. Add 4 to both sides. Negative 9x equals 18. And x equals negative 2. And once you have one variable, you can substitute negative 2 in for x into any one of the original equations and solve for y. So I'm going to pick the first one. That would be 3 times, instead of x, I'm going to put in negative 2 plus y equals negative 2. So that's negative 6 plus y equals negative 2. Add 6 to both sides. Y is equal to 4. And so your solution must be an ordered pair. It's the point where the two lines intersect. Just the two lines are written in standard form instead of slope-intercept form. Right? So my ordered pair, the point of intersection, if I were to graph these two lines, will be at negative 2, 4. And if you were to solve this problem by graphing, then you would rewrite both equations into y equals mx plus b, and then graph and find a point of intersection. And certainly if you want to check to see if negative 2, 4 is indeed a solution to the system, then you put negative 2 in for x and 4 in for y into both equations, and you gotta make sure that it makes both equations true. And then the third way of solving a system of equations, again algebraically, is by elimination, or sometimes called combination. So all we're doing here, just as the name implies, is we're trying to eliminate one of the variables. Either the x's or the y's, entirely up to you. Depending on the problem, it might be easier to do one or the other, or it might not matter. So we pick one variable that we want to eliminate, and then we try to create opposites. So for example, if I want to eliminate the x's, then I need these to be opposites. If this one down here is negative 3x, I want to make this one up here positive 3x. That way I can add them and they will cancel out. Alright, so we want to eliminate one of the variables and then combine the two equations into one equation and solve for the other variable. So here we could either multiply the top equation by 3 to get 3x and negative 3x, or we could multiply the bottom equation by negative 2 to get 2y and negative 2y, entirely up to you. I'm going to go ahead and choose to multiply the bottom equation by negative 2. That way it will give me opposites with the y's, and I'll be able to eliminate the y's, and it will also get rid of some of those negative numbers in my problem. So just remember that whatever you do to one term, you're going to do to all of the terms when you're multiplying. So I'm going to keep the first equation the same, x plus 2y equals 11, and then the second equation we're going to multiply, so that's going to give me positive 6x minus 2y equals 10, and then we're going to add them, and then notice what happens when I try to add them. I've got positive 2y and negative 2y, that adds to 0, they cancel out. So I have 1x plus 6x is 7x equals 21. Divide by 7, x is equal to 3. And then once you have one variable, then you again do as you did before, substitute it back in to one of the original equations and solve for the other variable. So I'm going to substitute it into the second equation. Negative 3 times, instead of x, I know x is 3, plus y equals negative 5. So that's negative 9 plus y equals negative 5. Add 9 to both sides, and y is equal to 4. And so my point of intersection, if I were to graph both of these lines, is going to be at 3, 4. Now I want you to pause the video for a minute and try example 1. There's two systems. I would like you to solve one using substitution and the other one using elimination. Up to you which one you want to do for which. So give it a try, and then you can skip forward in the video and check your work and see if you got the same answer. If you did, then you can move on, and if you didn't, then you can go back and watch how I did it. So here we're going to solve, I'm going to solve the first one using substitution. Okay, so the first thing I want to do is pick a variable to isolate. Pick an equation and then try to isolate a variable. So it looks like this y is the easiest one to get by itself. So I'm going to start with that one. 2x plus y equals 5. I'm going to minus 2x. And y is equal to 5 minus 2x. Again, doesn't matter if you write negative 2x plus 5. We're not graphing, so I don't have to write it into y equals mx plus b form. And then I'm going to take this 5 minus 2x, which is equal to y, and substitute it in for y in the second equation. You have to use both equations when you are doing substitution. Okay, so 4 times x plus 2 times, instead of y, 5 minus 2x equals 6. Distribute and solve for x, since I only have one equation with x. So 4x plus 10 minus 4x equals 6, and then something weird happens. When I try to combine like terms, my x's cancel out. 4x minus 4x is 0, and I get 10 equals 6, which is not true. This is a false statement. 10 does not equal 6. And so when your variables cancel out and you get a false statement, that means it doesn't matter what x is, right? This is always going to be false, and so there is no solution. If you rearrange these two equations into slope-intercept form and graph the two lines, you're going to see that they're going to be parallel lines. And even if you don't graph, if you rearrange it, if I try to rearrange it, looks like the first equation is y equals negative 2x plus 5, and the second equation is going to be 2y equals negative 4x plus 6, and then divide by 2, y equals negative 2x plus 3, and you can see that they have the exact same slope. And we know that parallel lines have the same slope. So if you're graphing, you'll rearrange it to slope-intercept form, and if you see the same slope but different y-intercepts, you know they're going to be parallel lines that will never intersect, and so there's no solution. Okay, and then the second one, I will use elimination. So what I'm going to do is I'm going to multiply the top equation by positive 2, and then I'll eliminate the x's. So let me rewrite this. We're going to have 2x plus 4y equals 20, and negative 2x minus 4y equals negative 20. And so I wanted to create opposites in my x's, which I did. So positive 2x minus 2x, that cancels out, but then the 4y plus negative 4y also cancels out, and I get 0 on the left. On the right side, 20 plus negative 20 is also 0. Okay, and now I have a statement that is true. So when we have a statement that is true, that means that there's going to be infinitely many solutions, because they overlap at so many points. It doesn't really matter what x is. This is different though, be careful. This is different from saying all real numbers. We don't want to say all real numbers as my solution. I just want to say that there are infinitely many solutions. And there's no symbol for that. Infinitely many solutions. The reason why it would not be correct to say all real numbers is because although you can say that x could be any number, y cannot be any number. Depending on what you pick for x, that determines the corresponding y value. So there are infinitely many points that are solutions, but not any point is a solution. Okay, so not all real numbers, just infinitely many solutions. When your variables cancel out and you get a true statement, there's infinitely many solutions to your system. If it's false, there's no solution. Otherwise, when you solve, you will have exactly one solution. Okay, so try the next example. Solve algebraically. It's a little bit more tricky. There's 3 variables. And again, I want you to pause the video, try it yourself first, and then skip ahead and see if you get the correct answer. And if you did, then you can move on, and if not, then rewind and watch how I did it. So the first thing I'm going to do, looks like the easiest variable to solve for is z, so I'm going to figure out what z is first. So I have z equals negative 4. So I've got that. Okay, and once you have z, we can simplify our other equations. I'm going to replace the z in my other 2 equation with the negative 4 since I already know what that is. So I'm going to rewrite this over here. I have x minus y minus z. Oh, let's replace the z with negative 4. So when I subtract negative 4, it's really a plus 4 equals negative 4. And I'm going to simplify by moving the constants to one side. So I'm going to minus 4 on both sides. X minus y equals negative 8. Okay, and I can't do anything else yet because I still have 2 unknowns. So I'm just going to leave this equation right here, and hopefully I can use it later. And then I'm going to do the same thing to my second equation. I'm going to rewrite it. So 5x minus 2y minus 3, instead of z, we're going to put a negative 4, equals 7. Simplify, 5x minus 2y plus 12 equals 7. And let's move the 12 over so that the constants are all on one side. 5x minus 2y equals negative 5 when I subtract 12. And again, I have an equation with two unknowns, so by itself, I can't solve that. But if I combine these two, I have a system of equations that I can solve, right? So we could do substitution or elimination, entirely up to you. If we want to do substitution, we can get the x by itself in the first equation by adding y to both sides. So I'm going to have x equals y minus 8. And then I can substitute. I'm going to take the y minus 8 and we're going to replace the x in the second equation with that. So 5 times y minus 8, and this becomes a problem just like what you did previously. Minus 2y equals negative 5. 5y minus 40 minus 2y equals negative 5. Combine like terms. 3y minus 40 equals negative 5. Oh, and I made a little mistake here. I forgot to write 5x. It should be plus 2y instead of minus 2y. So I'm going to put that in here. Plus 2y plus 2y. Okay, that's the original problem is plus 2y and I wrote minus. So instead of 3y, I should have, get rid of that, plus 2y plus 2y plus 2y. So now I should have 7y minus 40 equals negative 5. Add 40 to both sides. 7y is equal to 35. Divide both sides by 7, and y is equal to 5. Okay, so we got the other variable, and once we know that y is equal to 5, then I can put this back in here. X is equal to 5 minus 8, and so x is negative 3. And certainly you can substitute x equals negative 3, y equals 5, and z equals negative 4 into all three equations to see if it makes all three of them true, and it should. So your final solution is, instead of an ordered pair, because you had x and y before, now because we have three variables, we have an ordered triple. So that would be negative 3, ordered triple x, comma, y, comma, z. Negative 3, 5, negative 4. You've got an ordered triple. And if you were to graph this, then you would be graphing a point in 3D space. Okay, last example, an application problem. So again, see if you can start it and see how much you can go through, and then come back and look at the video. So we've got a candy manufacturer who wants to mix two types of candies to sell as Halloween mix candy bags. So those Halloween big candy mixes that you buy, somebody decided to do a candy mix, but because not all candies in those bags are worth the same amount, we have to decide how much should we throw in. So by itself, Reese's costs $2 a pound, and by itself, Hershey's are a lot cheaper, costs 75 cents a pound. Okay, so the candy manufacturer wants 1,000 pounds of the mixture. So he wants to mix Reese's and Hershey's, and he wants to make 1,000 pounds of the mixture. And then he's gonna sell this mixture by the pound. He's gonna sell it for $1.35 per pound. And so that obviously means that we're not gonna put in 50% Reese's and 50% Hershey's, right? So we have to figure out how many pounds of Reese's are we going to mix in and how many pounds of Hershey's are we going to mix in so that we can sell it for $1.35 per pound and make it worth the selling price, make it be worth the same amount of profit as if I was to sell them individually. So the first thing we want to do is define our variable. And your variables, your unknowns, is always what are they asking you for. So in this problem, they're asking you for how many pounds of each type of candy should we mix. So we're going to say x can represent, let x equal the number of pounds of Reese's that we're going to mix in, and we're going to let y equal the number of pounds of Hershey's. Okay, so once you define your variable, you're going to come up with a system of equations to model this situation using your variables. So x is how many pounds of Reese's we're going to mix in, y is how many pounds of Hershey's we're going to mix in. He wants 1,000 pounds total. So our first equation, so a little bit simpler than the second, is that however many pounds of Reese's plus however many pounds of Hershey's that we are putting into the mixture needs to equal exactly 1,000 pounds. So that's amount is set. The second equation, what else besides amount do they give me? They give me some prices, right? So the amount of how much the Reese's are worth in the mixture, how much all of the Reese's in the mixture costs would be $2 times however many pounds of Reese's we're mixing in. So $2 for 1 pound times however many pounds we're mixing in, plus we're also mixing in Hershey's, right? So Hershey's are 75 cents, so I'm going to put 0.75, so that's in terms of dollars, a pound, and we're going to multiply by however many pounds we put in. So 2x will be the cost of all of the Reese's in my mixture, and 0.75y will be the cost of all of the Hershey's in my mixture. And the total cost has to equal, we're going to sell it for $1.35 for 1 pound, but we have 1,000 pounds. Okay, so the second equation is about cost. So now we can solve the equation by substitution or elimination, entirely up to you. So I'm going to rewrite this. X plus y equals 1,000, my first equation. 2x plus 0.75, or you could change it to 3/4, entirely up to you. Y equals 1350, and then we can solve by substitution or elimination. So I'm going to go ahead and do elimination. I'm going to multiply the top equation by -2. Then I can eliminate my x's, and you can use your calculator if you want with the big numbers and the decimals. So that's going to give me -2x minus 2y equals -1,000. And then my second equation stays the same. And then we're going to go ahead and add them. And my 2x and -2x gets eliminated. And then I have -2 plus 0.75y, and that will give me -1.25y equals 350. I'm going to go back here because I forgot to distribute the 2 to the 1,000, so it should be -2,000. And then second equation stays the same. Sorry guys, doing this really late at night. go ahead and add, and these cancel out. All right, so that's better. So that's negative 1.25 y equals negative 650, and y equals, when I divide, I got 520. Okay, so then let's figure out x by substituting it back in. I'm going to pick the first one because it's a little easier. X plus y equals 1,000, and so x plus 520 equals 1,000. And subtract 520 and you get x equals 480. So that adds up to exactly 1,000 pounds. To answer the question, in any word problem, you have to answer the question that's being asked. So interpret your algebra, and if you're not sure what x and y stands for, go back and look up at how you define your variables, because you already defined that at the beginning. So he needs to mix in 480 pounds of Reese's and 520 pounds of Hershey's. Alright, in order to satisfy this condition. And then he will be able to sell it for $1.35 per pound, and he would make the same money as if he would sell them separately.